Even atoms that want to lose electrons, for reasons that we will talk about, have no choice but to attract their electrons. And this has to occur because their positive nucleus is always attracting their negatively charged electrons. Opposite charges attract, and opposite charges always attract each other. So ionization potential is the amount of energy required to remove electrons from an atom, including atoms that want to lose electrons because they're still holding on to them. So what is it that explains the pattern? Well, it's the same as electronegativity and very much the same as atomic radius. So when it comes to going across the table, you know that ionization potential increases. It gets progressively harder to remove electrons. Why? Because the nuclear positivity of the atoms is going up. So a stronger nucleus, a more positive nucleus, is better able to attract electrons. If there's more attraction between the nucleus and its electrons, it's going to take more energy for something to come along and steal one of those electrons. Going down the table, ionization potential decreases. So even though we know that cesium, with its 55 protons, is vastly more positive than the other two atoms on the chart, certainly more than the sodium, it still is easier to steal this outermost electron because it's just so far away. Why does the distance matter? Because the shielding effect is in play. So even though that nucleus is very, very nuclear positive and very strong, very capable at attracting electrons, we're talking about attracting an electron that's really far away from the nucleus. And that attractive force has to penetrate through all these layers of electrons and gets weaker and weaker every time that it does that. So by the time we reach this outermost electron, there's very little attractive force left over, and it becomes very easy to remove this electron from the atom.